Okay, students, Assalamu alaikum. And today, inshallah, we are going to start our next chapter and our next topics in fluid mechanics. Basically, if I remind you, or if you recall, we started with studying the fluid properties, and then we moved towards the study of the fluid mechanics. Now, when we started studying towards fluid mechanics, the first thing was to study the fluid statics. So we focused ourselves for the study of the fluid statics, and then we moved over to the fluid dynamics. Now, in studying the fluid dynamics, the first thing was that, so first chapter was the introduction, where we discuss about the fluid itself. What is a fluid? Then in second chapter was about the fluid properties. The third chapter was the start of the fluid mechanics, where we studied fluid statics. Then in fourth chapter, we studied about fluid dynamics, but in the fluid dynamics, the first thing to study is the fluid kinematics. So the fourth chapter was about the fluid kinematics. Then in the fifth chapter, we started with the fluid kinetics, where we initially developed the Reynolds transport theorem. We studied the Reynolds transport theorem, and I told you that the Reynolds transport theorem that we are developing in chapter number 5 is going to be used till chapter number 7. So in chapter number 5, we first developed the Reynolds transport theorem, and we applied it over the continuity equation. So this was chapter number 5, and from here onward, we started with the fluid kinetics. Then in chapter number 6, we applied the same Reynolds transport theorem for the momentum analysis of the fluid flows. Okay, and now what we are going to do is we are going to apply the Reynolds transport theorem for the energy analysis of the fluid flow. So basically, chapter number 5, 6, 7 belongs to fluid kinetics. Okay, so the structure was that chapter number 1, basic fundamentals about the fluid. Chapter number 2, fluid properties. 3, fluid statics. 4 was the fluid kinematics. Then 5, 6, 7 are fluid kinetics. Where in 5, we discuss about the continuity equation and the drive the general Reynolds transport theorem. In 6, applied the same Reynolds transport theorem over the momentum equations of the fluid flow. And in number 7, chapter number 7, we are going to apply the Reynolds transport theorem over the energy analysis of the fluid flow. So with the completion of till chapter number 7, we are actually done with the basic studies of the fluid mechanics. Okay, so this chapter is fundamental from the point of view that it is discussing the energy transformations within the fluid flow. So this is just the beginning of the chapter to just put you in perspective that where we are standing right now, where we started from, and where we are heading towards. Okay, and what is our current position in the course of the fluid mechanics. So this is lecture week 11 and 12. This is about the energy principle, where we apply the energy equation in the fluid flow problems. So our course outline for this chapter would include energy concepts related to energy, work, and power. These are not the new concepts. Most of these concepts you already taken in your secondary school, and then you are also taking it in the metric, inter, or O-level, A-level, whatever it is. And then also in relative courses of physics, even in your engineering. Then you have the conservation of energy. So conservation means to preserve something. Something is kept constant. Something is neither being created nor being destroyed. So when we said continuity equation, that was the conservation of mass. So we're saying that mass is not created, neither created nor destroyed. When we studied chapter number 6, we said conservation of momentum. When we say conservation of momentum, it means the momentum is neither created nor destroyed, but yes, momentum change forms. Okay, and now we will be talking about conservation of energy. In the same stand, we are going to say that energy can neither be created nor be destroyed, but it change forms. Okay, so this is something that we are going to discuss. Then we are going to talk about the energy equation, the basic energy equation that we are going to develop for the fluid flow problems. Obviously, whenever we are talking about any topic within this course, it is related to the fluid flow problems. Then we're going to discuss how the Bernoulli's equation that we developed in the chapter number 4 is linked with the energy equation that we develop here. So there are very obvious similarities of energy equation with the Bernoulli's equation, and that similarities we are going to discuss. Okay, then we're going to talk about the power equations, and then the mechanical efficiency, and then we'll talk about some transitions and the hydraulic and energy grid line. And with these topics, we are going to actually cover the entire the entire area of energy analysis within the fluid flow. So it's starting with some very basic concepts. I'm not going to spend a lot of time over that, but we'll just skim through some of the material so that you just know that we went through it. Energy, property of a system that characterizes the amount of work that the system matter can do on its environment. When we are talking about energy with respect to the fluid flows, so the biggest example or the most obvious example is the water behind a dam. So the energy that you get from the fluid flow, hydropower. Okay, so that is basically the one of the example of the fluid carrying energy. Then also we have the wind power. So wind also carries a lot of energy. We can run wind turbines. You can generate electricity using running the wind turbines. Okay, so wind has energy because it can be used to rotate the blades that are connected to a generator via shaft to produce electric power. Then we have gasoline. Gasoline is the petrol. So it's also in the fluid form, although what we do is that we don't directly use the fluid power of the gasoline, rather we combust it and we change its, we make it release its energy due to ignition or the combustion process. Okay. So anyways, these are some of the fluids through which we actually, which we use it for getting energy, for providing energy, for producing, for generating power. So energy classifications, basic classifications of energy is the mechanical energy, thermal energy, chemical energy, electrical energy, nuclear energy. Okay, these are some of the basic classifications of energy. Again, the descriptions are written here. You can go through these descriptions, but these are very basic information, nothing new. Units of energy. Unit of energy is joule, which is 1 Newton meter. So joule is 1 Newton meter. That is the energy associated with 1 Newton force acting through a distance of 1 meter. So if you have 1 Newton of force, which is actually acting or moving a distance of 1 meter, then we'll say that 1 joule of work has been done. So this is again one of the definitions that you have gone through earlier in different other courses, in the courses of physics. So we have other units of energy. For example, one British thermal unit is 778 foot-pound force, which is equals to 0.293 watt-hour, which is equals to 0.252 kilocalories, which is equals to 252 calories, which is equals to 1055 joules. Okay, so anyways, these are some of the conversions that we have here. The conversions you don't need to memorize. If it is needed, the conversion will be provided to you in the exam. Then we have, this is in the SI system. Then we have in the FPS system or the English unit system, we'll have 1 foot-pound force, which is equals to 1.35582 joules. Also, sometimes heat is referred in terms of the calorie. So 1 calorie is the amount of heat required to raise the temperature of 1 gram of water by 1 degree centigrade. So approximately about 4.187 joule. 1 calorie is about 4.187 joule. or 1 kilocalorie is 4187 joules. So these are some of the units of energy and the unit conversion shown here. Talking about the basic concepts of energy, we have energy in 2 or 3 different forms. The first form of energy is work. Okay, so work is done on a system when a force acts on a system over a certain distance. Okay, the effect of work is to increase the energy of the system. Magnitude of the work can be evaluated using. Again, this is a formula that you have studied earlier in your previous courses. Work has the same units as energy. So these are some of the examples mentioned here. You can go through those examples yourself. Then we have power. Power is the rate of doing work or using energy. So quantity of work over interval of time. So rate of anything is per unit time. So power is basically the rate of work. There are different forms of writing power. For example, one way of writing the power is force into velocity. There's also power. So we know that power is work over time. That's basically rate of work over time. But work is basically force into displacement over time. Okay. Now displacement over time is basically the velocity. So we can also write as power is equals to Fv. So force into velocity is also power. Or this is in the rectilinear motion. If it is in the angular motion, we can write power as torque into angular velocity. Units of power, again, these are the same units I already mentioned before. Typical values of power, you can go through it. These are some of the examples of this. In fluid flow, one of the device which is actually used to extract energy from the fluid and generate power is known as turbine. Now, turbine is a device which you have studied extensively in the course of thermodynamics before. So probably it's not a new concept to you. A turbine is a very complex device. We're not going to go into the construction of the turbine, but yes, it is one of the devices which actually uses the fluid power to produce energy, to produce, or it uses the fluid energy to produce power. So it is a machine that is used to extract energy from a flowing fluid. So we have a flowing fluid has some energy, it's going to extract that energy and convert it into power. For example, wind turbines, gas turbines, Pelton wheel, Kaplan wheel, Francis turbines. Some of the turbines are also there in our lab of the fluid mechanics, so you can also go through them. But anyways, all of these turbines, the basic function is to extract the energy from the fluid and convert it into mechanical power. Then the other thing is the pump. Pump is a thing which is actually opposite to turbine. We discussed this in the course of thermodynamics as well. Likewise, when we talk about turbines, turbine uses the fluid power, okay, and to produce or uses the flow energy of the flowing fluid to produce mechanical power, okay. On the other hand, pumps are opposite to it. In case of the pumps, mechanical power is used to actually add energy to the flowing fluid. Okay, so suppose if I want to raise the height or elevation of the fluid, I want to push the fluid from ground floor to the first floor. Okay, you know gravity acts downwards, so it's not. We need to do some work to push the fluid from ground floor to the first floor. So this could be done with the help of a pump. So pump is going to use the mechanical power. Now, how pump is going to generate the mechanical power? Obviously, pump is going to be connected with the motor. Motor is going to take electricity from the grid, and that electrical power will be converted into mechanical power of the pump, and then that mechanical power will be transmitted to the fluid. So the fluid is going to gain power, and we can raise the fluid, the elevation of the fluid from the ground floor to the first floor. Okay. So it's actually opposite to turbine. Turbine uses the the power of the flowing fluid and convert it into mechanical power. Pumps use the mechanical power and convert it and convert it into the power of the flowing fluid. So it is a machine that is used to provide energy to the flowing fluid. Turbine was extracting energy from flowing fluid. This pump is actually providing energy to the flowing fluid. Okay. So what is the difference between the pump and turbine? One basic key conceptual question that could be asked in the exam. What is the basic difference between the turbine and the pump? And what will be the answer? The turbine is a device which extract energy from the flowing fluid. Pump is a device which provide energy to the flowing fluid. That's the difference. Pump provide energy to the flowing fluid. How is it providing energy? You are connecting the pump with the electrical energy, with the electrical sockets. Okay, so the electrical grid energy that you take it from your national grid supply is used to provide energy to the flowing fluid, okay, with the help of pump. And turbine, on the other hand, you don't need to connect it to any electricity. Rather, if the fluid power is there, and you connect the fluid power with the turbine, it can run the generator and produce electricity. So it can extract the energy from the flowing fluid and convert it into mechanical energy, which can further be converted into electrical energy. So it's opposite. So the two are devices which are basically opposite to each other. One uses electrical energy to produce high pressure, other uses high pressure to produce electricity. So this is a basic question that could be asked in the exam, that what is the difference between the pump and the turbines? Anyways, this is basically a question of thermodynamics, but since the thermodynamics is a prerequisite here, so probably it is something that you should know. Okay, now let's talk about conservation of energy. Conservation of energy says that energy is conserved. Energy can neither be created nor be destroyed, but it changes forms. Now, there are different forms of energy. For example, we have work is a form of energy, and then the heat transfer is another form of energy. These are two of the forms through which any system interact with the surrounding. So you have a system, a fluid system, and obviously everything around that system is a surrounding. So the system interact with the surrounding by two ways. One way is by work, the other way is by heat transfer. And these are the two ways through which the energy interaction takes place at the boundary of the system. The first law of thermodynamics, you've already studied the first law of thermodynamics, which says that whatever is the change in energy of the system is equals to the net heat added to the system minus the net work done by the system. Okay, so you have a system, you have a fluid system, you added heat into the fluid system, and then that fluid system did some work. Okay, so what is the net change of energy in the system depends upon how much the energy was added into the system minus how much the work done by the system. Okay, so energy, heat energy, and the work are both the forms of energy interactions of the system with the surrounding. So delta E is equals to Q minus W. This is a basic formula that you have studied in the course of thermodynamics. So it's again an application of thermodynamics here within fluid mechanics. So first of thermodynamics, the equation is applicable when the system undergoes a process to move from state 1 to state 2. Here all terms have units of joules. Delta E is increase in energy stored in the system, which is equals to amount of energy that entered the system by heat transfer minus amount of energy that left the system due to work. Okay. And if the amount of energy entered the system is equals to the amount of energy that left the system, then the change in energy will be zero. Okay. There are certain sign conventions for W and Q, and these are already covered in the course of thermodynamics. So if we have this equation in the form of energy, joules, So if we divide this equation with time, we can get the equation in the rate format. So change in energy divided by time, so it will be rate of change of energy will be equals to rate of heat transfer, rate of heat added to the system minus rate of work done by the system. Okay, so when we say rate of heat added to the system, it will be just Q dot. You are adding a dot over the Q. And when we're saying net rate of work done by the system, it will be W dot. So we are adding a dot here just to mention that this is rate. And similarly, we can write here capital E dot as well, but it's better to write it here like dE by dt. So this is the same conservation of energy equation, but in the rate format. Now the question is that why do we need to write it in the form of in the rate format? Because now what we need to do is we need to apply the Reynolds transport theorem over energy, on energy. Okay, so if you remember, this is the Reynolds transport theorem that we actually developed in chapter number 5, and now we are in chapter number 7. And I told you at that time that when we are developing the Reynolds transport theorem in chapter number 5, that we will use it in chapter number 5 and chapter number 6 and chapter number 7. In chapter number 5, we used it for continuity equation. In chapter number 6, we used it for the momentum principle. And now in chapter number 7, we are going to use it for energy principle. Okay, so our extensive property here, which is B, capital B, control volume, the extensive property here will be the energy, the total energy of the system. Okay, and if our extensive property is the total energy, then the intensive property, small b, will be capital B by mass, which will be here E by mass, or you can say small e. Small e is the specific energy per unit mass. Okay, so this B will be actually the small e here. Okay, otherwise this is the same equation, which is the Reynolds transport theorem that we are going to now use and apply it over the energy. So if we apply it over the energy, now we are talking about the specific energy. Now energy, we have already discussed there are various forms of energies, but the three most usable forms of energy, which you have studied in the course of thermodynamics, are the kinetic energy, potential energy, and internal energy of any fluid. Okay, so we can write E as EK as the specific kinetic energy plus EP, which is the specific potential energy, and U as the internal energy. Okay, so since these are all the specific energies, so kinetic energy is basically half mv square. So when we are talking about specific, so m is going to be cancelled, so it will be just v square upon 2. Okay, potential energy is mgz. Okay, and when we're talking about specific, so m will be cancelled, so we're going to left up with gz only, and internal energy we just write as u. Okay, so our Reynolds transport theorem, when applied for energy, becomes like this. So d by dt equals to d by dt of the total energy of the system. So that's the change, rate of change of total energy of the system, is equals to the change in the energy within the control volume of the system plus the change which of in energy occurring at the control surface, which is occupying, which is surrounding the control volume. Okay, so this is the description of this equation for the Reynolds transport theorem. Okay, now here when we say that what is the change, what is the rate of change of energy in the system, so the first law of thermodynamics we already determined this. So this is the first law of thermodynamics, the rate equation. So dE by dt is basically q dot minus w dot, and this is what we are going to replace it here with. Basically q dot minus w dot. Okay, and here we have small e, we can substitute the small e, we can expand it and place all the terms. So it's basically v square upon 2 plus gz plus u. And here also we can write here v square upon 2 plus gz plus u. So our Reynolds transport theorem becomes like this. Okay. Now further, let's discuss a little more about here this W dot work. This is the net work done by the system. When we talk about the net work done by the system, so there are two forms of work which we are interested in. One is the shaft work, the other is the flow work. The shaft work is the work which is done by a shaft because of the rotation of the shaft. Okay, so either it is the case of the pump or the case of the turbine, it's always the shaft work. Okay, so the shaft work, we write it here as work of turbine minus work of pump. Okay, so work of turbine is whatever the work done by the turbines minus work of pump as whatever the work the input or the power provided to the pumps. So work of turbine minus work of pump will be the work of the shaft. Obviously, they two are opposite because work of turbine is the work extracted by the fluid flow, extracted from the fluid. Work extracted from the fluid is the work of turbines, and the work provided to the fluid is the work of pump. So the two are opposite in nature. So obviously one will be positive, other will be negative. Okay. So since we define W dot shaft as the net work output, so work of the turbine is considered as positive, and the work of the pump will then be considered as negative. It will be W dot T minus W dot P. Okay, then we have the work of the flow. Work of the flow is basically what? Work is force into displacement. Okay, and force can be written as pressure into area, and displacement can be written as velocity multiplied by time. Okay, so when we say about when we talk about rate of workflow, so it will be delta W by delta T. So it will be just PAV. Okay, if we divide by density and multiply by density, so this density into area into velocity, that becomes m dot, mass flow rate. Okay, so and mass flow rate can be written as rho v dot dA. Again, this is when we were developing the Reynolds transport theorem, we already discussed that how mass flow rate can be written as like this. Okay, so this is the form we are going to write the work of the rate of work for the case of flow. So if we substitute it into the main equation, so our main equation becomes like this. So we'll have Q minus work of shaft minus work of flow is equals to this is the rate of change of energy inside the control volume, and this is the energy going in and out of the control surface. So work of flow, if we substitute the value of work of flow from the previous equation, okay, so it can be added on the other side of the equation, okay, and we can then add them together in the control volume at the control surface integral. So the control surface integral becomes like this. Here we have internal energy plus pressure energy, and this is the term which is known as specific enthalpy. Specific internal energy plus specific pressure energy is known as specific enthalpy, and this is again something, the concept of enthalpy you have covered in the course of thermodynamics. Okay, so our base equation becomes like this: Q dot minus W shaft equals to d by dt integral v square upon 2 plus gz plus u, rho dv plus integral at the control surface v square upon 2 plus gz plus h, rho v dot dA. Further moving forward, suppose, and most of the time, the case that we are going to cover is for the case of a steady flow. If we have a steady flow, then there won't be any energy accumulation term. So there won't be any rate of change of energy inside the control volume. Okay, so if there is no change of energy in the control volume with time, so this accumulation term will get zero. Okay, so if we put this accumulation terms as zero, so what we are left up with, okay, now here this rho v dot dA we can write here as m dot, Okay. Okay, so when we are saying at the control surface, so we are taking the integral. Okay, so here this m dot would be all the mass flow going in as well as all the mass flow going out. Okay, but mass flow going in is always considered as negative. Okay, why mass flow going in is considered as negative? Again, this is something which we discussed in detail in chapter number 5, so don't need to explain it again. So all the mass flow going out are considered as positive, all the mass flow rate going in are considered as negative. So we can then write the equation in this format: Q dot minus W dot shaft equals to summation of all the mass flow rate going out into V square upon 2 plus GZ plus H minus summation of all the mass flow rate going in into V square upon 2 plus GZ plus H. Suppose if we have only a single inlet and single outlet, then this summation sign will be cancelled. Okay, and we are going to end up with this equation. So this is the case if we have steady flow and we have a single inlet and single outlet. Okay. Within the fluid flow. Now, there is one thing here that we are talking about the kinetic energy. When we are talking about kinetic energy, we are discussing about velocity. Okay, obviously kinetic velocity comes there inside the formula of kinetic energy. Now, which velocity we are discussing about? So suppose if I have a pipe and the fluid is flowing through the pipe, we know that there is a specific velocity profile, which is there is a specific velocity profile which is actually generated, and that velocity profile something looks like this, where the velocity is maximum in the center and at the edges the velocity is 0, because the edges of the pipe, suppose the pipe is stationary, so because of the no slip condition at the edges, the layers of the fluid which are there at the edges are also stationary, and the layer of the fluid which is in the center is basically is having the maximum velocity. So we'll have a V max here, okay, and we'll have V minimum, which is actually 0 at the edges. So which velocity we are considering here? It's not V max, it's not V0. Okay, so which velocity we are considering? We are considering here the mean velocity. We're considering here the mean velocity, where a hypothetical value of velocity which is going to have the same effect as the actual velocity. Okay, but this hypothetical velocity is going to be uniform throughout the entire cross section. Okay, so what we do is that we apply a correction factor. We apply a correction factor. Okay, and that correction factor is alpha. So this is how we do it. So we'll have the mean velocity here, V1 mean, V2 mean, and apply the correction factor alpha 1 and alpha 2. Okay. Now the formula for this correction factor will be 1 upon A integral V upon V V average power cube dA. This is the formula for finding out the correction factor, which is basically the mean correction factor. This alpha at alpha equals to 1 when the velocity is uniform across the section. For most cases of turbulent flow, alpha is approximately equals to 1.05. Since most of the cases that we normally deal are the cases where the flow is turbulent. And in case of the turbulent flows, alpha is approximately 1.05. So we can actually consider alpha as 1 for most of the cases. Okay. And therefore, it is a common practice in engineering application to let alpha is equals to 1. But alpha is basically what? Alpha is the correction factor. Correction factor for mean velocity. Okay, we are using a mean velocity, but in reality, there won't be the mean velocity. Okay, there will be some, so there will be some variation in the velocity from the top edge to the bottom edge. Okay, so alpha is basically the correction factor for this. Sorry? In the alpha formula, V is basically the formula for variation of velocity across the section. Okay, so here V will be the actual velocity variation across the section. Okay, so if the velocity is varying along y-axis and x-axis, then V should be a function of x and y-axis. If the velocity is varying along the radius, then V should be a function of the radius. So it will always be a function of something. That's why we have dA here. So depending upon how we are taking our differential area, we will have a formula for the V. Okay. So V is the actual velocity distribution across that cross-sectional area. Okay, now let's have a small problem. Okay, before going through the small problem, do you want a break of 5 to 10 minutes? Let's have a break of 10 minutes and then we're going to start with this problem. Okay, so let's see this numerical problem where we have kinetic energy correction factor for laminar flow. The velocity distribution for laminar flow in a pipe is given by the equation V equals to V max 1 minus R over R naught power square. Where R naught is the radius of the pipe and R is the radial distance from the center from the center. Find the kinetic energy correction factor. So this is alpha that we need to find here in this problem. So here in the diagram, it shows that how the velocity profile is. The velocity profile and the equation for the velocity profile is provided here. This is the actual velocity profile. Vmax is the maximum velocity in the center. And the radius is taken from the center. So velocity variation from the center with respect to R is given. So here V is given as a function of R. Where Vmax is a constant and R naught is the actual radius of the pipe, which is also constant. So these two are constants. So we need to find what is the kinetic energy correction factor, alpha. Okay. So for the case of kinetic energy correction factor, the base formula is the same which you have seen before. This is the formula for alpha. It's 1 upon area integral of V, actually V as a function of R given, by V mean whole power cube into dA. Okay. Now in this, V as a function of R is given, but we need to first find what is V mean. Okay. So in order to find V mean, we have the formula for V mean as this. This is the formula for V mean, which you studied in chapter number 5. When we discussed about the rate of flow, we discussed that what is the formula for V mean. So this is we studied in chapter number 5, this formula. So V bar is 1 upon area integral VdA. Now V is given as a function of R. dA will be 2 pi R dr. This will be dA. Okay. And V is given as a function of R. This is V max 1 minus R square upon R naught square. Okay, so here what we need to do is we need to integrate it from 0 to R naught over the entire radius, over the entire pipe. That's 0 to R naught. So we take the constants out of the integral, then we integrate, and after integrating, we apply the limits. And once we apply the limits, we get the final answer as this. So here, some of the terms are going to cancel, and we're going to end up with V max over 2. So this is just simple mathematics. Okay, so go through it yourself. If there is any step which is not clear, you can come back to me, or rather not come back to me, because it is just simple integration. So this is basically V mean. Now we have V mean, we can apply it into the formula for alpha. Okay. So again, the actual area is, because the radius is R naught, so area is pi R naught square. Okay, so this is the area. Okay. Then if you see here, V mean is basically V max over 2, and V max is a constant. So basically V mean is also a constant value, is going to come out of the integral. And inside the integral, we'll have V cube into 2 pi R dr. Again, we are going to substitute the value of V, because V was given as a function of R given in the question. So we substitute this thing, Okay, and then after that, we are going to solve it, apply the integration from 0 to R naught, apply the limits from 0 to R naught, okay, and solve it. Here, to evaluate the integral, make a change of variable by letting u equals to 1 minus r squared over r naught squared. These are just the methodology of solving the integral. There are multiple ways of solving the integral, the way you want to solve it. But in any ways, from this onward, if you solve the integral, you're going to end up with the answer as 2. Alpha will come out to be 2 in this case. So if you know the velocity profile, then you can substitute the values within the, you can substitute the velocity profile equation within the formula for kinetic energy correction factor, and you can actually find out what is the kinetic energy correction factor. Here, the kinetic energy correction factor is coming out to be 2. Okay, it's because this is a laminar flow. For the case of turbulent flows, normally the kinetic energy correction factor is around 1.05. Okay, so we kindly consider it as 1 in the main equation. Is the solution clear? Is there anything which is not clear within the solution? Okay, so we were discussing the simplified form of the energy principle equation. The last simplified form of the energy principle equation that we came up with is this. This is the simplified form of the energy equation, energy principle equation. Now, what we can do is we can write this equation in the form of head. Now, you remember when we started fluid statics, we said that we can write equations in the form of pressures, where the all terms will be in the pressure units, or we can write it in the form of head. Okay, so we had a piezometric head, we had the elevation head, we had kinetic head, okay, we had hydrostatic head. These are all the heads that you have studied before. Okay, so similarly, now here we have it in the form of power. So if we divide the power by the weight per unit time of the flowing fluid, we're going to still get the value in the form of head. So we can also write the equation in the form of head. So when we talk about the shaft work is basically the turbine work minus the pump work. But for this case, we can have the turbine head and the pump head. We'll call it turbine head and pump head. So for the case of pump head, it will be pump work divided by m dot g, okay, which is basically the weight per unit time of the flowing fluid. And when we talk about the turbine head, it's again the work of the turbine divided by m dot g. So that will be the turbine head. So that will be the head added by the pump. This will be the head removed by the turbine. Head added by the pump, because pump is taking out the electricity and putting energy into the fluid. Turbine is actually taking the energy from the fluid, converting it into mechanical work output. So the two are doing opposite things. Okay. So whenever it's case of the case of the pump, we say that energy or the head added by the pump. Whenever it's case of the turbine, we say that's energy of the head removed by the turbine. Okay, so this is added, this is removed. Okay, so if we write the whole equation in the form of head, okay, so the same equation is going to come out to be like this. We'll have P1 over gamma plus alpha 1 V1 square upon 2G plus Z1 plus HP, which is the pump head, plus P2 upon gamma plus alpha 2 plus V2 square upon 2G plus Z2 plus HT. HP is the pump head, HT is the turbine head, okay, plus this term, where you have the change in the internal energy from point 1 to point 2 and the heat added in the system. Okay, now most of the time, whenever the fluid is flowing through a pipe, the heat added within the system is because of the viscous effects, because the different layers of the fluid, when they move against each other, so there is friction. Even in solids, if you move two solids against each other, you will find friction, and that friction converts some of the work energy into heat. And so if I rub my hands together, okay, so I'll feel that my hands are getting hot. Okay, so friction causes generation of heat. So the same thing happens in the case of the fluid flow in the pipe as well. As the fluid is flowing within the pipe, there is viscous effects. Viscous effects is there at the boundaries. Okay, and because of the viscous effects, heat is added. Because of the friction, heat is added. Viscous effects is the friction within the fluid. So when the heat is added, that heat actually enters into the fluid. Okay, so basically this is known as head loss. Because of the viscous effects, this is known as head loss, this term. So why we call it head loss? Because the heat, because the energy, which was the fluid energy, which has now been converted into heat because of friction, is now lost. Initially, it was inside the fluid and it was in the form of a pressure, can do some useful work. Now it has been converted into heat and raised the temperature of the fluid a little, and that's it. Now we can never take it back. Okay, so for example, if I have energy in my hands, I can do some work with that. So when I rub my hands together and some of the energy is being converted into heat, that heat energy is lost. I can never take it back. Okay, so similarly, the heat energy generated due to the viscous effects, within the pipe flows, within the fluid flows, that energy is actually lost. Okay, so we call it head loss. Okay, so loss in the form of head. Okay, so we call it head loss. So last term enclosed in square brackets in the above equation represents energy loss due to viscous action between fluid particles and due to heat transfer. It is simply referred to as head loss and represented by HL. Okay, it is always positive because of the second law of thermodynamics. Okay, why it's always positive? Because losses will always be there in the system. You studied in thermodynamics that you cannot have a system without losses. So that was the second law of thermodynamics. So you cannot have an ideal system where there are no losses. So losses will always be there. So if the losses are always there in the system, that means there will always be head loss. So there will always be a little amount of heat. Maybe that heat generation, because of the viscous effects, is so small that it does not change the temperature of the fluid considerably. Maybe the change in the temperature, maybe the fluid was at 24 degree. Now the fluid temperature is 24.00000001. This change is negligible, but it is there. Okay, so head losses will be there. And because of the head losses, there will be change in temperature. You might say that that change in temperature is negligible, but still it is there. Okay, so so it is always positive because of the second law of thermodynamics. Okay, so this last term is basically the head loss, and thus the final form of the energy equation becomes this. So this is the final form of the energy equation, which will be provided to you in the exam. Whenever you have to solve the problem using energy equation, the basic energy equation for fluid flows, which will be provided to you in the exam, is this. Okay, this is the most advanced form of the energy equation for fluid flows. Now let's analyze each one of the terms within this equation, or each of the term one by one within this equation. So we are saying that suppose there is a fluid flow, and if this fluid is a continuous medium, let's say this is 0.1 and let's say this is 0.2, and we are saying that we can apply the energy equation from 0.1 to 0.2. And what we are saying is that what is the basic idea of this equation? That the total energy is conserved. So whatever is the total energy at 0.1 is the same as the total energy at 0.2. But the energy change forms. Maybe at 0.1 there was some hydrostatic energy, hydrostatic pressure energy, part of it has been converted into elevation energy, part of it might be converted into kinetic energy, might be converted because of the pump, might be extracted by the turbine. Okay, so might be converted into heat because of the friction, because of the viscous effects. But the thing is that if we are taking into account each and every factor, then the overall energy in the system remains same. So whatever is the overall energy at 1 is the same as the overall energy at 2. This is the idea. Okay, so you have to understand one thing. How do we proceed it? Okay, so initially we talked about fluid statics when there was no fluid motion at all. And we say we develop the equation, which is the hydrostatic equation. Okay, then after that we say that now we are moving towards fluid kinetics. But let's first talk about a case when the fluid itself is not moving, but the container in which the fluid is there, that is moving. Okay, so we developed the equation, and that equation was known as the Euler's equation. Then we further proceeded. We said, okay, now it's not just the container moving, it's actually the fluid in motion. But we are considering for specific case when there are no viscous effects. So for the inviscid flow, steady flow, okay, and we along the streamline. So we applied 4 conditions, and by applying those 4 conditions, 4 restrictions, okay, we said that, okay, now the fluid is in motion, but with these 4 restrictions, this is the Bernoulli's equation. Now in the final format, we are saying that now we are also considering the viscous effects. In the Bernoulli's equation, we ignored the viscous effects, but now we are considering the viscous effects. Okay, and now we are considering all other factors. Still we are keeping it steady flow. Still we are keeping it along the streamline. But the condition of viscous effects, we are going to remove that. And now this is the energy equation. So energy equation is a further modified form of the Bernoulli's equation in that sense. Okay, so if you remember in case of the Bernoulli's equation, what do we had? We had the hydrostatic pressure head. We had the kinetic head, we had the elevation head. Okay, we were not talking anything about the pump, we are not talking anything about the turbine, and since the viscous effects were not there, so there was no heat loss, there was no head loss. Okay, so at state point 2, we had the hydrostatic head, we had the kinetic head, we had the elevation head. Okay, and we were also not discussing anything about a kinetic energy correction factor. Okay, because viscous effects were not there, so we were assuming that all layers are moving at the same velocity, so kinetic energy correction factor was not needed in that position. Okay, so if you remove alpha 1, or if you put alpha 1 and alpha 2 as 1, and if you remove HP, HT, and HL, this becomes basically the Bernoulli's equation. Okay, but now we are actually including all those terms which we were previously ignoring, all those factors which we were ignoring. So this is the complete form of the equation, which is basically the energy equation. So in this energy equation, this is the pressure head plus velocity head plus elevation head. Or pressure head plus elevation head is also known as piezometric head. Piezometric head plus velocity head. Or velocity head is also known as dynamic head. And velocity head is also known as kinetic head. Okay, plus pump head. Okay, is equals to pressure head plus velocity head plus elevation head at point 2 plus turbine head plus head loss. Head loss is because of the viscous effects. Okay, so the thing is that this equation, as I told you, will be provided to you in the exam, but what each term presents will not be provided. So conceptually, what could be asked in the exam? Conceptually, you could be asked, what is head loss? Define head loss. So the head loss are basically the losses in the fluid because of the viscous effects. This will be the answer. What is head loss? Head loss are basically the losses in the fluid because of the viscous effects. Okay, what is turbine head? So if we are externally adding energy into the fluid, so from point 1 to point 2, we have a turbine in between, and the turbine is adding additional energy into the fluid. That's the turbine head. What is pump head? Okay, if we have a pump which is actually extracting energy from the fluid. Okay, so from 1 to 2, as the fluid is moving from 1 to 2, there is pump in between. So pump is actually taking some of the energy from the fluid. So it will be negative HP from as we move from 1 to 2. So if you take it on the other side of the equation, it becomes plus HP. So pump head is basically the energy or the head extracted by the pump from the fluid. Turbine head is the energy or the head added to the fluid by the turbine. Head loss will always be in the side of the losses. So head loss is the energy removed from the fluid because of the viscous effects as the fluid moves from 1 to 2. Okay, and at 1 we'll have the piezometric head or the pressure, hydrostatic pressure head plus elevation head plus the velocity head, and at 2 we'll have the piezometric head, which is the pressure head plus the hydrostatic pressure head plus elevation head plus the dynamic and or the kinetic head. Okay, and if we have the kinetic energy correction factor needed, kinetic energy correction factor is only needed if the flow is laminar. If it is turbulent, normally it is not needed. Okay, so this thing you could be asked in each and every term, what does that term represent, is something that could be asked in the exam as short question, conceptual question. Okay, so the equation will be provided to you, but what does each term represent? This thing will not be given. So this thing is something that will be asked, that define this term. Okay, so if I said that if it is laminar flow, or if I say that if it is turbulent flow, how would you modify this equation? What change will occur in this equation if it is turbulent flow? So alpha 1 and alpha 2 will become 1. Okay, if there is no pump in the fluid flow, so what change will occur? HP will become 0. If there is no turbine in the fluid flow from 1 to 2, what change will occur? HT will become 0. Okay, suppose if it is if it is an inviscid flow, the viscous effects are not there, what change will occur? HL will become 0. Right? If the fluid elevation is not changing, then Z1 will be equal to Z2. If the fluid velocity is not changing from 1 to 2, then V1 will be equals to V2. If the fluid hydrostatic pressure is not changing, then P1 will be equals to P2. If the piezometric head remains same from 1 to 2, that means P1 upon gamma plus Z1 will be equal to P2 upon gamma plus Z2. These are some of the things I can make different variations and ask you that what change is going to occur under these conditions in this equation. So this equation will be provided to you in the exam, but what does each term means and how does each term is going to be affected based on the provided condition is something that you should understand, you should know, will not be provided in the exam. Okay, so clearly mentioned that what could come from this in the exam. What could you expect? Okay, so if you are surprised, then your fault. Okay, so power, head and power is, if we have the head, we can find out the power, or if we have the power, we can find out the head. The formula for it is this. Okay, as we did here back when we were discussing about the turbine work, or the pump work, we said that the pump head will be pump work divided by m dot g. So what will be pump work? It will be pump head multiplied by m dot g. Right? So the same way is written here. M dot g multiplied by the head is going to give us the power. Okay? M dot g multiplied by the head is going to give us the power. And this thing is also same as gamma QH. How is it same as gamma QH? You can find out because you see, what's the formula for density? Density is mass over volume. So it is equals to mass flow rate over volume flow rate. Okay. So that means mass flow rate is equals to density into volume flow rate. So I can write here as density into volume flow rate multiplied by G multiplied by H. Okay. Now here density multiplied by G is basically gamma. So gamma QH. This is the formula. The same formula. Okay. So P equals to m dot GH is equals to gamma QH. How to convert power into head if the mass flow rate is given? How to convert power into head is if the volume flow rate is given. If the mass flow rate is given, this will be the formula. If the volume flow rate is given, this will be the formula. These two formulas will not be provided in exam. These two formulas will not be provided in exam. So you have to memorize. Okay. So far, everything is clear? I hope it is clear. Okay, so let's move over to this problem. We're going to solve this problem only, and then we are going to end our class today. Okay. And we're going to take from here onwards in the next class. Okay, so a horizontal pipe carries cooling water at 10 degrees centigrade. For a thermal power plant from a reservoir as shown, the head loss in the pipe is given as this. This is the formula for head loss. It's 0.02 multiplied by length divided by diameter into velocity square divided by 2g, where L is the length of the pipe from the reservoir to the point in question. V is the mean velocity in the pipe, and D is the diameter of the pipe. If the pipe diameter is 20 centimeter, so this is given, D is given, and the rate of flow is 0.06 meter cube per second. So this is rate of flow, 0.06 meter cube per second. Do you think it is volume flow rate or mass flow rate? 0.06 volume flow rate, because meter cube per second. If it was mass flow rate, it should be kg per second. This is what I told you in chapter number 5, that sometimes in the question it's written as rate of flow or flow rate, but it is basically the mass flow rate. Sometimes it is volume flow rate. How you're going to recognize? Check the units. Okay, so here it is 0.06 meter cube per second. It's basically cube. What is the pressure in the pipe at L equals to? So length is given as 2000. Okay, assume alpha 2 is equals to 1. Okay, so this is the situation we have. We have a container here. So let's have a look here. So we have a container here. This container is open to atmosphere. Okay, and the elevation of this, the water in the container is, the elevation of it is about 100 meter. Then at the bottom of the container, near the bottom, when the elevation is 20 meter, you have a pipe connected. And this pipe is actually taking the water from the container. Okay, and it is taking water to a distance of 2000 meter. Length is 2000 meter. Okay, and what do we need to find out? We need to find out what is the pressure in the pipe at L equals to 200 meter. At this point, what is the pressure? This is what we need to find out. Okay, so once again, read the question. The horizontal pipe is horizontal, carries cooling water at 10 degree for a thermal power plant from a reservoir. This is a reservoir. The head loss in the pipe. Okay, obviously the fluid will be flowing in the pipe, so there will be head loss. So head loss is provided. Okay, this is the head loss. Okay, it's a function of length, diameter, velocity. These are the factors which it depends upon. Okay, well, L is the length of the pipe, V is the mean velocity, D is the diameter. If the pipe diameter is 20 centimeters, so diameter is provided of this pipe. They provided, and the length and the rate of flow is 0.06 meter cube per second. So rate of flow is also provided. This flow rate Q is also provided. What is the pressure in the pipe at L equals to 2,000 meters. This is what we need to find out. So at this point 2, what is the pressure in the pipe? So before moving towards the solution of the problem, first, do you understand the problem statement? Okay. So if we understand the problem statement, now it's time to move towards the solution of the problem. So, okay, how do we know that we have to apply the energy equation? One thing is very clear: whenever the fluid is moving in a pipe, and a pipe has a small diameter, you cannot ignore the viscous effects. You can ignore the viscous effects in this region. This is the region where you can ignore viscous effects. But here you cannot ignore the viscous effects. Okay, so it's too proximity, too close to the pipe. And pipe is stationary, fluid is moving. The layers of fluid, there will be relative motion between the layers of the fluid. Cannot ignore friction, cannot ignore viscous effects. Okay, similarly, if the fluid motion was considered in this region or this region, again, viscous effects cannot be ignored. But in the central region, you can ignore viscous effects because all the layers are moving almost in the same speed. Okay, so first of all, you cannot apply Bernoulli's equation here because the pipe length, the major flow is within the pipe length. You cannot ignore that. Okay, and because of this, the head loss is provided. If the viscous effects was not there, head loss would be 0. If the viscous effects were not there, head loss would be 0. But here we have viscous effects, so head loss is not 0. Okay, since the head loss is not 0, so you have to consider the viscous effects, and so you cannot use Bernoulli's equation. Bernoulli's equation is for inviscid flow. So now we are only left up with the option of energy equation. So we're going to deal with the energy equation. Okay, so this is how you recognize that this problem needs to be solved using the energy equation. Now let's have a look at the energy equation. This is the energy equation. So we are going to apply it between 2 points. Obviously, it should be a continuous medium. Continuous water should be there from point 1 to point 2 all throughout. Okay, so point 1, we can take it here at the top of the reservoir because this is a point where most of the parameters are known. And point 2, we can take it at the point where we want to find out the pressure. Okay, so our energy equation will be P1 upon gamma plus alpha 1 V1 square upon 2G plus Z1 plus HP equals to P2 upon gamma plus alpha 2 V2 square upon 2G plus Z2 plus HT plus HL. So this is the formula that will be provided to you in the exam, as I told you. So now let's look at each and every one of the terms. So let's look at about point 1. Point 1 is the top of the reservoir. It is open to atmosphere. You see here, this is a small inverted triangle, which shows that it is open to atmosphere. If it is open to atmosphere, then the gauge pressure will be 0. So P1 is 0. Okay, so this thing is here. Okay, from point 1 to point 2, do you see any pump in between? There is no pump. So pump head, 0. Do you see any turbine in here from 1 to 2? No turbine. So turbine is 0. Okay. Okay. At point 1, it is the top of the reservoir, and point 2 is inside the pipe. So point 2 is going to have a huge velocity compared to point 1. Do you have any question? The reason is that P1 is open to atmosphere, and whenever it is open to atmosphere, the gauge pressure is 0. We are taking into account the gauge pressures. Okay. Okay. So V1, the velocity, V1 is basically the change in the level of water in the tank. It will be very, very slow compared to the velocity of the fluid in the pipe at 2. And when this difference is too much, then their squares will be too much big difference. Okay, so V1 is very small, so V1 square will be very small compared to V2 square. So basically we can ignore V1, consider it to be 0, assume it to be 0, because V1 is very small than V2. Okay. We don't know what is Z1. We don't know what is Z2. No, we know it actually. It was given in the question. What is elevation head at Z1? What is elevation head at Z2? So we know what is Z1. We know what is Z2, right? P2 is something that we need to find. Alpha 2 was given in the question as 1. Okay, so this thing is basically 1. Okay, HL, we don't know, but we know the formula for HL. Formula for HL is 0.002. Length is given 2000. Diameter is given, but again velocity we don't know. So we don't know velocity here in this formula for HL. So if we know the velocity, and also we need the velocity here. Okay, and these two velocities will be same, because HL, when we are using it, it is at 0.2. So this is 0.2. So actually HL, when we are using it, is at 0.2. So the velocity here in the formula for HL will also be V2. Okay, but another information that we have is Q, volume flow rate, and we know that Q is equals to AV. Okay, or you can say A2 V2. Okay, so if we know Q, and we can find A2, why? Because we know the diameter. So if we know diameter, you can use this information to find what is A2. Okay, so you have A2, you have Q, you can find what is V2. And once we have V2, then you can substitute here, you can find what is HL. And you can substitute V2 here. Eventually, there is only one unknown, which is P2, that you can find. Okay. So this is substituting all the values. First finding V2. Okay, then finding HL, substituting it into the main equation, finding P2. The P2 comes out to be 418 kilopascal. Okay. If suppose it was a Bernoulli's equation, if suppose we say that it is inviscid flow, so what change would occur? Head loss will not be there. And if head loss is not there, then what change will occur? So you will find out, you're going to find out that the value of P2 will be different. Okay. So the value of P2 that you're going to get by using Bernoulli's equation will be different than the value of P2 that you're getting from this energy equation. So which one is more accurate? Energy equation more accurate, because in real world, viscous effects will be there. In Bernoulli's, we made the assumption that the viscous effects are not there. Okay, so this thing is not done here, but could be asked in the exam. And I give you this problem and you solve it the way it is solved here. And then I ask you that to consider if the flow is inviscid, then what will be the pressure at 0.2? And see the difference. How much is the difference in the pressure if you consider it as an inviscid flow, or if you solve it using an inviscid flow assumption, or if you consider the viscous effects as well. So how much is the difference? So find out the percentage difference in the pressure because of that. So it's going to give us the idea that what is the effect of viscosity in this problem. Okay, so this is something that could be asked in the question. This is the modification. Okay, we are going to stop at this point here, and in the next class we're going to start from the power equations, and inshallah we're going to finish this energy principle application within the fluid flow problems. Okay, so far if there is anything which is not clear to anybody, please feel free to ask.